is excited about photography or videography? Yeah? The title of the talk kind of gives it away. Okay, we are waiting for the last people to come in and take a seat. Last time, raise your hands if you have a free seat next to you. Everyone of you coming in, look for a raised hand, take your seat, and then we will start. Yeah, very good. Okay, looks like the doors are finally closed. Okay. So the next talk on the second day is about ultrafast imaging. So many of you have done videography or photography, have thought about exposure time, how fast you can do your photography, and some of you might have played with lasers and have built blinky stuff with it or have done scientific experiments. Caroline will now show us what it happens if we take those two, combine them, and take it to the extreme. Caroline is working at DESI since 4 years. She's done her PhD and is now working in a group for theoretical fast modeling of inner workings of molecules and atoms. She is doing computational work and working together with experimentalists to verify their observations, and now she's presenting the inner mechanics of what she is doing and how we can actually maybe photograph molecules while they are forming. Applause.
Great. Yeah, thank you very much for the introduction, and thank you very much for having me here. I'm excited to see this room so full. So I'm going to speak today about an ultra-short history of ultra-fast imaging. It's a really broad topic, and I'm just going to present some highlights, some background. Before I start, I'd like to give you a few more words about myself. As we've already heard, I work at DESI. This is the DESI campus you see here. And in the Center for Free Electron Laser Science, circuit in orange, that's where I did my PhD. So this whole campus is located in Hamburg. This is probably also a familiar place to many of you. And now this year we are in Leipzig, a bit further away for the 36th Congress. So I'd like to start with a very broad question. What is the goal of ultrafast imaging? And we've heard already that ultrafast imaging is related to photography. Now, as many of you know, when you take a picture with a quite long exposure time, you see just a blurry image. For example, in this picture of a bowl of water, we can hardly see anything. It looks a bit foggy. But if we choose a correct exposure time, which in this case is 100 times shorter in the right picture than in the left picture, then we see a clear image, and we can see dynamics unfold. So we have here a drop of water that is bouncing back from the bowl, and also some ripples that are forming on the surface of this bowl. This is only visible because we chose the right exposure time. And this is, to me, really the key of being successful in ultrafast imaging, to take a clear picture of an object that is moving. But it's not enough to take just a picture. So now imagine you're a sports reporter. You get these two pictures, and you're supposed to write up what happened. So it's complicated. So the top picture is the start, the bottom picture is the end. Just from these two pictures, it's hard to see. But if we see the full picture, we can see very complex dynamics unfold. There are particles accelerating at high velocity, coming in from the back. And even particles we did not see in the first picture at all somehow are very relevant to our motion. And not only skiing races are very dynamic, but most processes in nature are also not static. This is true for everything we see around ourselves, but it's especially true for everything that is quite small in the microcosm. And in general, we can gain a lot more insight from time-resolved images, so from ultra-short movies. I'd like to show you the very first ultrafast movie that was ever taken, or maybe even the first movie that was taken at all. This guy, Edward Muybridge, lived in the 19th century, And very shortly after the invention of a photography method, he tried to answer the question, does a galloping horse ever lift all of its feet off the ground while it's running? To us, it may seem like not so important question, but in the 19th century, the horse was the main method of transportation, and horse races were very popular. So there was a lot of interest in studying the dynamics of a horse. And this process is too fast to see with the naked eye, but Muybridge implemented a stop-motion technique where the horse, as it is running, cuts some wires that then trigger photographs. And with this, he was able to take these 12 photographs of the horse in motion that was published under this title in Stanford in the 19th century. And we see very clearly in the top row, third picture, and maybe also second picture, that indeed the horse lifts all of its legs off the ground, which was a new insight at that time. And when we stitch all of these snapshots together, we have an ultra-fast movie of a horse galloping, which might be seen as the first movie that was ever made in the history of mankind. Now, when I say ultra-fast today, I'm no longer thinking about horses, but about smaller things and faster things. But let's go there very gently. So the time scale that we are all familiar with, that we can see with the naked eye, is something of the order of seconds. So for example, the acceleration of this cheetah we can see with the naked eye. Now, if we zoom in on this motion, we see that there are muscles inside of the animal that are contracting as it is running. And this muscle contraction takes place within milliseconds, so that's a part of 1,000 in 1 second. But we can go even smaller than that, to the microsecond. So proteins inside of the muscles or in any biological matter fold and unfold on a timescale of microseconds. That's already a part in a million of a second. Now, going even smaller to nanoseconds, there's certain dynamics that take place within these proteins, for example, how they dissolve in water. But the timescale that I'm interested in today is the femtosecond. It's even faster than that. It's the timescale where individual atoms move in molecules, as shown in this animation. Now, a femtosecond is very short. It's a part in a million of a billion of a second, or as we physicists like to call it, 10 to the minus 15 seconds, because that's easier to spell. We can, to us, we can go even faster than that. The timescale of electronic motion in molecules would be the attosecond. I'm just mentioning it here because we don't stop at molecules, but nature is even faster than that. But for the purpose of this talk, I will mainly focus on processes that take place within the femtosecond, so within 10 to the minus 15 seconds. Now, this timescale is something that is not really related to what we think about in everyday life. But there are certain processes in chemistry, biology, and physics that are really fundamental and that start at this timescale. Just to give you an idea how short a femtosecond is, the width of a human hair is about 100 micrometer. It's shown here in an electron microscopic picture. And for light, at the speed of light, it takes only 30 femtoseconds to cross the hair. So that's how fast a femtosecond is. And even although this timescale is so short, there are many important processes that start here. I'd like to mention just two of them. The first one is vision. In our eyes and our retina, there sits a molecule called rhodopsin that is shown here to the left. And when light hits rhodopsin, it starts to isomerize, which is a fancy word for saying it changes its shape. And this transmits, in the end, electrical impulses to our brain, which enables us to see. And this very first step of vision takes only 200 femtoseconds to complete. But without it, vision would not be possible. Another very fast process that is fundamental in nature is photosynthesis, where plants take light and CO2 and convert it to other things, among them oxygen. And the very first excitation, where light hits the plant and it starts to make all this energy available, that also takes less than 100 femtoseconds to complete. So really the fundamental questions of life lie at this timescale. And I'd like to just mention that all of these processes are not only very fast, but they also take place in very small objects that are of the size of few atoms to nanometers, which makes it also hard to observe because we cannot see them with a naked eye or with standard microscopes. Now, we've seen already that it's important to choose the right exposure time to get a clear image of something that is moving. But the kind of method that we need for taking such a photograph of something that is moving depends a lot on the time scale. So for stuff that is moving within seconds or fractions of a second, we can see that with the naked eye. We can use cameras to resolve faster motion, pretty much like Muybridge did with the very first camera. Today, of course, we can go much faster to maybe a few microseconds. With very fancy cameras called optoelectronic streak cameras, I won't go into detail here, we can go down to picoseconds. So we are already very close to the motion of molecules, but we are not quite there yet. The timescale that we want to investigate is the femtosecond, so really a timescale of molecular motion, and electronics are not fast enough to reach this timescale. So we need something new. And fortunately, we can create light pulses that serve as, to say, flashes that take snapshots of our moving molecules with femtosecond time resolution. And light pulses can be made so short. So in the following, I'm going to show you a bit more detail on how we can use these ultra-short light pulses to take snapshots of moving molecules. The first method that I would like to briefly show you is X-ray diffraction, where we have an ultra-short pulse, an X-ray pulse, coming in. It hits a sample, shown here as the red bubbles. That's essentially a molecule that we just place in the beam. And it produces a so-called diffraction pattern that we can then record on a screen. Now, the whole process is quite complicated, so I'd like to just sketch the very basics of it. We see here X-ray radiation hitting a crystalline sample here to the left, and the sample is excited, starts to radiate X-rays back, and on the right we can see the X-rays leaving the sample again. They will interfere, and we can record this pattern on the screen. So this is what we see here in this visualization to the right. With this, we can feed a reconstruction algorithm that allows us to transform back our diffraction pattern that we've seen here for in this case, a biomolecule. We can reconstruct from that the image as it was in real space. So this is some protein, I believe. X-ray diffraction is very nice for resolving small structures with atomic detail. Another method how we can take snapshots using ultra-short pulses that I would like to briefly introduce is absorption spectroscopy. Now, you may know that light contains several colors. For example, you surely have held a prism in hand, and the prism can break white light up into all the colors of a rainbow that we can see with the eye. Now, we can do the same with X-ray pulses, then we cannot see the colors anymore, so let's just stick with a prism here. When we place a molecule in front of all these colors, the molecule will block certain colors. That's quantum mechanics. You just have to believe it, or learn about it in long studies. So the molecule is placed in front of all these colors, and to the right, the absorption spectrum is recorded. And the parts of the spectrum that are very bright correspond to the colors that have been blocked by the molecule. And this is a very nice technique to investigate ultra-short dynamics, because where these lines are located is characteristic of the chemical elements that we find in the molecule. For example, if we use X-ray radiation for this specific molecule that I've shown here, glycine, it's not so important which molecule it is, we have 3 different atoms in this molecule that are important, carbon, nitrogen, and oxygen, and they absorb at very different colors, so we can keep them apart when we take the spectrum. But not only that, we can take the spectrum at a later time when the molecule has moved around a bit, and we will see that the colors, the position of the lines have changed a tiny bit. So it's really not much, and I exaggerated it already in this visualization quite a bit. But with experimental methods, we can resolve this, and this allows us to then trace back to how the molecule was moving in between when we took these 2 snapshots. There are many more methods that you can use to take ultra-fast images. So we call them probe signals because we probe the ultrafast motion of a molecule with such an ultrashort pulse. For example, we can record photoelectrons, or we can record fragments of a molecule, and many more. But I won't go into further detail here because this is a non-exhaustive list of methods that we can use. I'd rather like to show you how we can take molecular movies, so how we can combine all these ultrashort pulses to, in the end, film a molecule in action. Now, we've already seen in the movie of the horse that we need to stitch several snapshots together, and then we have a full picture, full motion of a molecule. So we just like to do the same, but 10 to the 15 times faster. Should not be too difficult, right? So we use our ultrashort pulse. First ultrashort pulse that we use is a trigger pulse that sets off the motion in the molecule. This defines as a certain time zero in our experiment and makes it sort of repeatable because we always start the same kind of motion by giving it a small hit. And now it's just moving around. So we wait for a certain time, a time delay, and then come in with a probe pulse. The probe pulse takes a snapshot of a molecule. This goes to some detector, goes to a kind of complicated reconstruction method that we just execute from our screen. And with this, we reconstruct a snapshot of a molecule. But this is only one snapshot, and we want a whole movie. So we need to repeat this process over and over again by shining in more and more probe pulses. And this will create more and more snapshots of a molecule. And in the end, we could stitch all of these together, and we would arrive at the same image that you see in the middle, where the molecule is happily moving around. There's one little problem. The probe pulse typically destroys the molecule. This is very different. This is very different from taking pictures of a horse. The horse normally survives. So the probe pulse destroys the molecule. It just goes away. So for each of these snapshots, we need to use a new molecule. So we typically have a stream of samples that is falling from the top to the bottom in our experiment. And then we have to carefully align two pulses, a trigger pulse and a probe pulse, that come together and take a snapshot of this molecule. And of course, we have to find a method on how to make identical molecules available in, you see there's a lot of complications with doing these experiments that I'm completely leaving out here. So now we want to take a molecular movie. And we know that we want to have ultrashort pulses to do so. But I didn't tell you yet what kind of light source we need. So there are many light sources all around us. We have here light from lamps. I have a light in my laser pointer. We have light from the sun. But we need quite specific light sources to take these snapshots of molecular motion. We've already established that we want ultrashort pulses because else we cannot resolve femtosecond dynamics. But for the kind of wavelength that we need, I would like to quickly remind you of the electromagnetic spectrum that you've probably seen at some point in high school or so. So light, as you see here in the bottom picture, is an electromagnetic wave that comes in different wavelengths. They can be quite long, as in the case of radio waves to the very left. Then we have the region of visible light shown here as the rainbow that we can perceive with our eyes. And then we have wavelengths that are too short to see with our eyes. First, UV radiation that gives us a tan in the summer if we leave our house. And then we have X-ray radiation, soft and hard X-ray radiation that have atomic wavelengths. So the wavelength is really on the order of the size of an atom. So what kind of wavelength do we need to study ultrashort dynamics, ultrafast dynamics? We can first think about what kind of wavelength we need when we want to construct an ultrashort pulse. I've drawn here two pulses. To the left, a slightly longer pulse. To the right, a shorter pulse. And now, if you think about squeezing the left pulse together such that it becomes shorter and shorter, you see visually that the wavelength also needs to shrink. So we need shorter wavelengths for the shorter the pulse we want to make. So this will be located somewhere here in this region of the electromagnetic spectrum. And another important thing that we need to keep in mind is if we want to take pictures by X-ray diffraction, we are limited. So we can only resolve structures that are of about the same size as the wavelength we used to take our diffraction image. So if we want to take a picture of something with atomic resolution, our wavelength needs to be of atomic size as well. And this places us in the region of X-rays, drawn here, but have a wavelength of less than a nanometer. So we can establish that we want small wavelengths in general. We have two additional requirements that I will just touch upon very briefly. First, we need very brilliant pulses. Because the pulses are so short, we need to have a lot of light in the short pulse. You can think about taking a picture in a dark room with a bad camera, you won't see anything. So we need very bright flashes of light. Another requirement is we need coherent laser light. So we cannot just use any light, but it needs to have certain properties like laser light. Unfortunately, the lasers that you can buy commercially do not operate in the region of the electromagnetic spectrum that we are interested in. So we need to come up with something new. And I will show you how we can generate ultrashort pulses, both in the laboratory, where we can generate pulses that are very short and extend up to maybe the soft X-ray region. And another method to generate ultrashort pulses is at free electron laser sources, where we can go really to the hard X-ray regime. But first, I'd like to go to the laboratory. So in the laboratory, it's possible to generate an ultrashort pulse by using a process that's called high harmonic generation. In high harmonic generation, we start off with a high intensity pulse, that's the red pulse coming in from the left, which is focused in a gas cell. And from there, it generates new frequencies of light. So the light that comes out is no longer red, but it's violet, blue. We cannot see it with the naked eye, so that's an artist's impression of how high harmonic generation works. Before going into more detail about why this method is so good at producing ultrashort pulses, I'd like to mention that this is only possible because we have the high intensity driving pulses, the red laser pulses, available. This goes back to work by Donald Strickland and Gérard Mourou, who were awarded the Nobel Prize in the year 2018 in physics for this work that has been done in the 80s. Now we're coming to the only equation of this talk, which is this equation that relates the energy width and the time duration of an ultrashort pulse. By the law of Fourier limits, we cannot have pulses that are very short in time and at the same time very narrow in energy. But we need to choose one. So if we want to have pulses that are very short in time, like the pulse that I've shown here on the bottom, that is actually only 250 attoseconds long, so even shorter than a femtosecond, then we need to have a very broad width in energy. And this means combining a lot of different colors inside of this pulse. And this is what makes high harmonic generation so efficient at creating ultrashort pulses, because the spectrum, the colors that come out of high harmonic generation are shown here, and they really span a long width. So we get a lot of different colors with about the same intensity, and you can think of it like putting them all back together into one attosecond pulse that is very short in time. This method has really made a big breakthrough in the generation of ultrashort laser pulses. We see here a plot of the time duration of laser pulses versus the year. And we see that since the invention of the laser here in the mid-60s, there was a first technological progress, and shorter pulses could be generated. But then in the 80s, there was a limit that had been reached of about 5 femtoseconds, I believe. And we could not really go farther than that. And only with high harmonic generation that sets in here shortly before the year 2000, we were able to generate pulses that are of a femtosecond duration, so that really touch the timescale of molecular motion. The current world record is a pulse that is only 43 attoseconds long, established in the year 2017. So that's really the timescale of electrons, and we can do all sorts of nice experiments with it where we directly observe electronic motion in atoms and molecules. This is all very nice, but it has one limitation. We cannot go to hard X-rays, at least not right now. So high harmonic generation cannot produce the kind of very short wavelengths that we need in order to do X-ray diffraction experiments with atomic resolution. So if we want to have ultra-short pulses that have X-ray wavelengths, we need to build, right now, very complex, very big machines, the so-called free electron lasers. Now, this would be a specific light source that can produce ultra-short pulses with X-ray wavelengths. In itself, the X-ray wavelengths is not so new. We know how to take X-ray images for about 130 years. And already in the 50s, Rosalind Franklin, who's looking at a microscope here, was able to take a picture of DNA, an X-ray diffraction pattern of the DNA double helix that was successful in revealing the double helix structure of our genetic code. But this is not a time-resolved measurement. So think of it as you have a molecule that is in crystalline form, so it's not moving around, and we can just take an X-ray image of it. It's not going anywhere. But if we want to take a picture of something that is moving, we need to have very short pulses, but we still need the same number of what we call photons, light particles. Or think of it as we need more brilliant X-ray flashes of light than we could obtain before. And there was very nice technological development in the past 50 years or so, where we were able to go from the X-ray tube to newer light sources called synchrotrons and today free electron lasers that always increase the peak brilliance in an exponential way. So we can take really brilliant, really bright X-ray flashes right now. I cannot go into the details of all of that, but I found a very nice talk from 2 years ago that actually explains everything from synchrotrons to FELs, still available online if you're interested in this work. And as always, if something is scaling exponentially, most of you will be familiar with Moore's law that tells us about the exponential scaling of transistors. If something grows this fast, it really opens up a new series of experiments, of new technological applications that no one has thought of before. And the same is true with free electron lasers. So I'm going to focus just on the most brilliant light sources for X-rays right now. The free electron lasers that are at the top right here of this graph have been around for maybe 10 years or so. I cannot go into a lot of detail on how to generate ultra-short pulses with X-rays, so I'd like to give you just a very broad picture of how this works. First, we need a bunch of electrons that is accelerated to relativistic speed. This sounds very easy, but is actually part of a 2-kilometer-long accelerator that we have to build and maintain. Now we have this bunch here of electrons shown in red, and it's really fast. And now we can bring it into something that is called an undulator, that is a series of alternating magnets, shown here in green and blue for the alternating magnet. And you may remember that when we put an electron, that is a charged particle, into a magnetic field, the Lorentz force will drive it away. And if you have alternating magnets, then the electron will go on a sort of wiggly path in this undulator. And the electron is a charged particle. As it is wiggling around, whenever it turns around, it will emit radiation that happens to be in the X-ray region of the electromagnetic spectrum, which is exactly what we want. We can watch this little movie here to see a better picture. So this is the undulator seen from the side. We now go inside of the undulator. We have a series of alternating magnets. Now the electron bunch shows up, and you see the wiggly motion as it passes the different magnets. And you see the bright X-ray flash that is formed and gets stronger and stronger as the electron bunch passes the undulator. So we need several of these magnet pairs to, in the end, get the very bright X-ray flash. And at the end of the undulator, we dump the electron. We don't really need this electron bunch anymore, and continue with the very bright X-ray flash. This whole process is a bit stochastic in nature, but it's amplifying itself in the course of the undulator. This is why the longer the undulator is, the more bright X-ray flashes we can generate. This whole thing is kind of complicated to build. It's a very complex machine. So right now, there are only very few free electron lasers in the world. There's one in California called LCS1, currently being upgraded to LCS2. There are several in Europe. There's one in Switzerland, in Italy, in Hamburg. So there's a flash that does not operate in the hard X-ray regime, but was the kind of first free electron laser. There's the most recent addition to the free electron laser zoo. It's the European XFEL, also located in Hamburg. And then we have some of these light sources in Asia, in Korea, South Korea, Japan, and one currently under construction in Shanghai. I'd like to show you a bit more details about the European X-ray free electron laser, because it's closest to us, and at least closest to where I work. So the European XFEL is a 3.4 kilometer long machine that is funded by in total 12 countries. So with Germany and Russia paying the most, and then the other 10 countries also providing to the construction and maintenance costs. This machine starts at the DESY campus that is shown here to the right of the picture. And then we have first an accelerator line for the electrons that is already 1.7 kilometers long, and where electrons reach their relativistic speed. Then the undulator comes in, so the range of magnets, where the X-ray flashes are produced. The X-ray flashes then cross the border to Schleswig-Holstein, shown here. On the other side, in a new federal state, they reach the experimental hall. We have in total 6 experimental end stations at the European XFEL that provide different instrumentation depending on which kind of system you want to study. You need slightly different instruments. And it's not only for taking molecular movies, but the XFEL is used, among others, for material science, for the imaging of biomolecules, for femtosecond chemistry, all sorts of things. So really wide range of applications. It's right now the fastest such light source. It can take 27,000 flashes per second, which is great because every flash is one picture. So if you want to take a lot of snapshots, if you want to generate a lot of data in a short time, it's great to have as many flashes per second as possible. And as you can imagine, it's kind of expensive since there are so few free electron lasers in the world to take measurements there. The complete price tag for constructing this machine, it took 8 years and cost 1.2 billion euros, which may seem a lot, but it's the same amount that we spend on concert halls in Hamburg. So kind of comparable. Now, when you factor in maintenance and so on, I think a minute of X-ray beam at such an XFEL costs several thousands of tens of thousands of euros in the end. So getting measurement time there is complicated, and there are committees that select the most fruitful approaches and so on. So in order not to waste our dear taxpayers' money. With this, I'd like to make a small comparison of the light sources that I've introduced now. So I introduced the laboratory light sources and the XFEL light source. In general, in the laboratory, we can generate very short pulses of less than 100 attoseconds by now. In the XFEL, we are limited to something about 10 femtoseconds right now. In terms of brilliance, the XFELs can go to much more bright pulses, simply because they are bigger machines, and high harmonic generation in itself is a kind of inefficient process. In terms of wavelength, X-ray free electron lasers enable us to reach these very short wavelengths, the X-rays that we need to get atomic resolution of diffractive images. In the laboratory, we are a bit more limited to maybe the soft X-ray region. There's another important thing to keep in mind when we do experiments, that's the control of pulse parameters. So is every pulse that comes out of my machine the same as the one that came out of my machine before? And since the XFEL produces pulses by what is in the end a stochastic process, that's not really the case. So the control of pulse parameters is not really given. This is much better in the laboratory. And in terms of cost and availability, it would of course be nice if we could do more experiments in the lab than at the XFEL, simply because the XFEL is so expensive to build and maintain, and we have so few of them in the world. And you can see this tunnel here. It stretches for 2 kilometers or so, all packed with very expensive equipment. So I'd like to show you a brief example of what we can learn in ultrafast science. So this is theoretical work that we did in our group, so no experimental data, but still nice to see. This is concerned with an organic solar cell. So we all know solar cells, they convert sunlight to electric energy that we can use in our devices. The nice thing about organic solar cells is that they are foldable, very lightweight, and we can produce them cheaply. The way that such a solar cell works is we have light shining in, and at the bottom of the solar cell there sits an electrode that collects all the charges and creates an electric current. Now light creates a charge that somehow needs to travel down there to this electrode, and in fact many of these charges. So the important thing when we build such an organic solar cell is that we need a way to efficiently transport these charges. And we can do so by putting polymers inside. So polymer is just a molecule that is made up of two or more different smaller molecules. And one such polymer that should be very efficient at transporting these charges is BT1T, that is shown here. The name is not so important, it's an abbreviation. Because in BT1T, when we create a charge at one end of a molecule, here at the top, it travels very quickly to the other side of a molecule. And you can imagine stacking several of these BT1Ts, or especially of the Ts, together, putting it in this material, and then we have a very efficient flow of energy in our organic solar cell. So what we did was we calculated the ultrafast charge migration in BT1T, shown here to the right. The pink thing is the charge density that was created by an initial ionization of the molecule. And now I'll show you the movie, how this charge is moving around in the molecule. So you can see the individual atoms moving, the whole molecule is vibrating a bit. And the charge, if you look closely, is locating on the right half of the molecule within about 250 femtoseconds. Now, we cannot observe this charge migration directly by looking at this pink charge density that I've drawn here, because it's, at least for us, not experimentally observable directly. So we need an indirect measurement. And X-ray absorption spectroscopy that I showed you in the beginning could be such a measurement. Because in the X-ray absorption spectrum of BT1T, that I've shown here in the bottom left, we see distinct peaks depending on where the charge is located. Initially, the charge is located at the top sulfur atom here in this molecule, and we will see a peak at this color. Once the charge moves away to the bottom of the molecule, to the other half, we will see a peak at the place where nothing is right now because the charge is not there. But if I start this movie, we will again see very fast charge transfer. So within about 200 femtoseconds, the charge goes from one end of the molecule to the other end of the molecule. And it would be really nice to see this in action in a future XFEL experiment, but the process is very long. You need to apply for time at an XFEL. You need to evaluate all the data, so maybe a couple of years from now we will have the data available. Right now we are stuck with this movie that we calculated. Now, towards the end of my talk, I'd like to go beyond the molecular movie. So I've shown you now how to generate the light pulses and an example of what we can study with these light pulses, but this is not all we can do. So when you think of a chemical reaction, you might remember high school chemistry as something like this, which is always foaming and exploding and nobody really knows what is going on. So a chemical reaction, quite naturally, involves molecular dynamics. For example, in the decomposition of a molecule, to go from here, from the left side to the right side, the molecules will somehow need to rearrange, so all the atoms will have moved quite a bit. We've seen already how we can trigger these chemical reactions or these molecular motion. That was part of a molecular movie. But it would be really cool if we could control the reaction with light. So the way to do this, it's not currently something that is possible, but maybe in the near future, would be to implement a sort of optimization feedback loop. So we would record the fragments of our reaction, send it to an optimization routine that will also be quite complicated and will need to take into account the whole theory of how light and matter interact and so on. And this optimization routine would then generate a new sequence of ultrashort pulses. And with this feedback loop, it might be possible to find the right pulses to control chemical reactions, taking into account the quantum nature of this motion and so on. Right now, this is not possible, first because the whole process of how we can generate these ultrashort pulses is not so well controlled that we could actually implement it in such a loop. And also the step optimization routine is more complex than it looks like here in this picture. So this is something that people are working on at the moment. But this would be something like the ultra-fast wish list for next Christmas, not this Christmas. So we've succeeded in taking the molecular movie, but we would also like to be able to direct the molecular movie. So to go beyond just watching nature, but controlling nature, because this is what humans like to do best. Fortunately or unfortunately, it depends. So I'd like to just show you that this is really an ultra-fast developing field. There's lots of new research papers every day, every week, coming in, studying all sorts of systems. When you just take a quick and dirty metric of how important ultra-fast science is, this is the number of articles per year that mention ultra-fast in Google Scholar. It's exponentially growing. At the same time, the number of total publications in Google Scholar is more or less constant. So the blue line here outgrows the green line considerably since about 10 years. So what remains to be done? We've seen that we have light sources available to generate ultrashort pulses, but as always, when you have better machines, bigger machines, you can take more fancy experiments. So it would be really nice to develop both lab-based sources and free electron laser sources so that we can take more interesting, more complex experiments. Another important challenge, that is what people in my research group where I work are working on, is to improve theoretical calculations. Because I did not go into a lot of detail on how to calculate these things, but it's essentially quantum mechanics. And quantum mechanics scales very unfavorably. So going from a very small molecule, like this glycine molecule here, to something like a protein is not doable. Simply, you cannot compute this with quantum mechanics. So we need all sorts of new methodology to better describe larger systems. We would, in general, like to study not only small molecules and not only take movies of small molecules, but really study large systems, like this is the FMO complex that is central in photosynthesis, or solid states that are here shown in this crystalline structure, simply because this is more interesting for biological, for chemical applications. And finally, as I've shown you, it would be cool to directly control chemical reactions with light. So to find a way how to replace this mess with a clean light pulse. With this, I'm at the end. I'd like to quickly summarize. Femtosecond dynamics are really fundamental in biology, chemistry, and physics. So more or less the origin of life is on this timescale. We can take molecular movies with ultrashort laser pulses, and we can generate these pulses in the laboratory or at free electron lasers with different characteristics. And we would like to not only understand these ultra-fast phenomena, but we would also like to be able to control them in the future. With this, I'd like to thank you for your attention and thank the supporting institutions here that funded my PhD work.
Well, that was an interesting talk. I enjoyed it very much. I guess this will spark some questions. If you want to ask Caroline a question, please line up behind the microphones. We have 3 in the aisles in between the seats. If you want to leave, please do so in the door here in the front. And until we get questions from the audience, do we have questions from the internet?
Yes, Big Fat Random User is curious about the design of the X-ray detector. Do you have any information on that?
That's also very complex. I'm not a big expert in detectors. At this point, I'd really recommend watching the talk from 2 years ago that explained a lot more about the X-ray detectors. What I know about the X-ray detector is that it's very complicated to process all the data, because when you have 27,000 flashes of light, it produces, I think, terabytes of data within seconds, and you need to somehow be able to store them and analyze them. So there's also a lot of technology involved in the design of these detectors. Yeah.
Thank you. So the first question from microphone 2 in the middle.
So my question is...
Please go close to the microphone.
My question is regarding the synchronization of the detector units when you're pointing to free electron lasers, how you can achieve this synchronization.
This is also very complicated. It's easier to do in the lab. You're talking about the synchronization of essentially the first pulse and the second pulse, right?
Yes.
So in the lab, you typically generate the second pulse from part of the first pulse. So you have a very natural alignment, at least in time, of these 2 pulses. The X-ray free electron lasers have special timing tools that allow you to find out how much is the time delay between your 2 pulses. But it's true that this is complicated to achieve, and this limits the experimental time resolution to something that is even larger than the time duration of the pulses.
So now next question from microphone number 3.
Yes. I remember in the beginning you explained that your measuring method, your pulse, usually destroys your molecules. That's a bit of a contradiction to your idea to control.
In principle, yes. But so in the case of control, we would like to use a second pulse that does not destroy the molecule, but, for example, or at least destroys it in a controlled way. For example, so there's a difference between just blowing up your molecule and breaking apart a certain part that we are interested in. And that's what we would like to do in the control case. So we would like to be able to control, for example, the fragmentation of a molecule such that we only get the important part out and everything else just goes away. Yeah.
Okay, thank you.
So then another question from microphone 2 in the middle.
So thank you for the talk. I was interested in how large structures or molecules can you imagine with this laboratory conditions and with this X-FEL thing?
Sorry, can you repeat? I didn't.
So how large molecules can you do imaging in this laboratory with this high Hammer
how
lasers?
large? So how large is not really the fundamental problem. People have taken snapshots of viruses or bigger biomolecules. If you want to, the problem is rather how small can we get. So to take pictures of a very small molecule, currently we cannot take a picture of an individual small molecule, but what people do is they create crystals of a small molecule, stacking several of them together, and then taking images of this whole crystal. For single particles, I think right now about the scale of a virus, nanometers.
Thank you.
Okay, do we have another question from the internet?
We have. So this is concerning your permanent destruction of forces, I guess. How do you isolate single atoms or molecules for analyzing between the different exposures?
Yes, excellent question. So molecules can be made available in the gas phase by, so if you have them in a solid somewhere and you heat that up, they will evaporate from that surface. This is how you can get them in the gas phase. This, of course, assumes that you have a molecule that is actually stable in the gas phase, which is not true for all molecules. And then the hard thing is to align all three things. So the pump parts, the probe parts, and the molecule all need to be there at the same time. There are people doing whole PhD theses on how to design gas nozzles that can provide this stream of molecules. Yeah.
So you're basically really having a stream coming from a nozzle
Yes.
with a very thin stream, I guess, and
Yes.
then you're exposing it like in
Yeah.
a regular interval.
And of course, you try to hit as many molecules as possible. So this is especially important when you do pictures of crystallized molecules, because crystallizing these molecules is a lot of work. You don't want to waste like 99% that just fall away and you never take snapshots of them.
Thanks.
So another question from microphone 3.
So, how do you construct this movie? I mean, for every pulse you have a new molecule, and for every molecule is oriented differently in space and has different oscillation modes. How do you correlate them? I mean, in a movie. I mean, every molecule is different at the previous one. How
Yes,
can
excellent
construct a
question.
movie?
That's so first, what people can do is align molecules. So especially molecules that are more or less linear, you can force them to be oriented in a certain way. And then there's also a bit of a secret in the trigger pulse that first sets off this motion. For example, if this trigger pulse is a very strong photoionization, then this will kill off any sorts of vibrational states that you have had before in the molecule. So in this sense, the trigger pulse really defines a time zero that should be reproducible for any molecule that shows up in this stream. And the rest is statistics. Yeah.
Thank you.
So there's another question on microphone 3.
Are there any pre-pulses or ghosts you need to get rid of?
Sorry, again?
You have to control pre-pulses or ghosts during this effect for measuring?
That I'm not really sure of, since I'm not really conducting experiments, but probably.
And another one from the middle, from microphone 2, please.
I suppose if you apply for experimentation time at the X-FEL laser, you have to submit very detailed plans and timelines and everything. And you will get a time window for your experiment, I guess. What's going to happen if you're not completely finished within that time window? Are there easy possibilities to extend the time, or do they just say, well, you had your 3 weeks, you are out, apply in 2026?
Yeah, I think it's the regular case that you're not finished with your experiments by the time your beam time ends. That's how it usually goes. It's also unfortunately not 3 weeks, but it's rather like 60 hours delivered in 5 shifts of 12 hours. So yeah, you write a very detailed proposal of what you would like to do, submit it to a panel of experts, both scientists and technicians. So they decide, is it interesting enough from a scientific point of view, and is it feasible from a technical point of view? And then once you are there, you more or less set up your experiment and do as much as you can. If you want to come back, you need to submit an additional proposal. So yeah, I think most experimental groups try to have several of these proposals running at the same time, so that there's not a 2-year delay between your data acquisition, but yes, no possibility to extend. It's booked already for the complete next year. The schedule is fixed. Yeah.
Thank you.
So I don't see any more people queuing up. If you want to pose a question, please do so now. In the meantime, I would ask the Signal Angel if there's another question from the internet.
Another question about the dimensions of all those machines. The undulator seems to be rather long and contain a lot of magnets. Do you have an idea how long it is and how many of those electromagnets are in there?
Yes, sorry, I didn't mention it. It's about, I think, 170 meters long in the case of a European XFEL. I'm not sure about the dimension of the individual magnets, but it's probably also in the hundreds of magnet pairs.
So is there more? Excuse me, there's a question on the microphone to number 3.
Yep. Hi. It's regarding the harmonic light
Please go closer to the microphone.
The harmonic light generator that you were showing at the very beginning, just before the one that won the Nobel Prize. Can you also produce light in the visible range, or it has to be in the invisible range?
The high harmonic generation. So in the visible range, you cannot create pulses that are so short that they would be interesting for what I'm doing. The pulse that comes in is already quite short, so it's already femtoseconds long. They just convert it into something that is fractions of a femtosecond long. And yeah, in the visible range, that's kind of the limit how short your pulse can be.
So it's not a good candidate for hyperspectral imaging light source, no? You need another kind of technique, I guess.
Well, I mean, you're just kind of limited what short pulses you can generate with which wavelength. Yeah.
Thank you.
So again, a question to the single angel. Are there more questions from the internet?
I have another one about the lifetime of the molecules in the beam.
Mm-hmm.
How fast are they degrading, or how fast are they destructed?
So probably the question is about how fast they are destructed before. So either before our pulses hit the molecule. The molecules should be stable enough to survive in the gas phase from the point where they are evaporated until the point where the pump and the probe parts come together, because otherwise it does not make sense to study this molecule in the gas phase. When the probe parts hits and it flows apart, I guess picoseconds until the whole molecule is really
like
out.
Instantaneous.
Yeah.
So I don't see any more questions on the microphones, and we have a few minutes left. So if there are more questions from the internet, we can take maybe 1 or 2 more.
Give me a second.
For people leaving already, please look if you have taken trash and bottles with you.
So there's one very, very technical question. How do you compensate the electronic signal, that the electronic signal reaction is probably slower than X-ray or light or spectrum changes at one moment, or at one particular moment? That was interesting to analyze. I don't understand the question, though you may.
I think I understand the question, but I don't have the answer because, again, see, that's the problem of speaking to a technical audience. You get all of these very technical questions. The data analysis is not instantaneous, so the data is transported somewhere safe in my imagination and then taken from there. So this data analysis does not have to take place on the same timescale as the data acquisition, which I guess is also because of the problem that was mentioned in the question. Yeah.
I might interrupt here. Maybe it's also about the signal transmission, like the signal rising of the signal, electrical signal transmissions, because this would probably require bandwidths of several megahertz, gigahertz, I don't know, to transport these very fast results.
Yeah, I think that's also a problem of constructing the right detector. That has been solved, apparently, because they can take these images.
And on the other hand, we have 10 gigabit Ethernet, so we get faster and faster electronics. More questions from the internet? Does not look like it. Also, the time is running out. So let's thank Caroline for her marvelous talk.